think modern bridge design is the only thing that prevents train disasters? Think again. On the 29th of December 1876, a railroad bridge collapsed under the weight of a train in Ashtabula, Ohio. The disaster killed approximately 92 people, though some estimates reached 200. What made this catastrophe unique was that it combined engineering failure, design flaws, and lack of maintenance into a single moment of disaster. While we focus on preventing train collisions today, we've largely forgotten about preventing bridge failures, yet the lessons of Ashtabula remain profoundly relevant. Today, you're going to discover what went wrong with that bridge and why this disaster mattered. Get ready to understand why Victorian engineers learned hard lessons about the consequences of experimental design. The 29th of December 1876. A cold winter night in Ashtabula, Ohio. A passenger train carrying about 150 to 200 people was crossing a bridge over the Ashtabula River when the structure suddenly gave way beneath them. The train plunged into the frozen river below. Passengers tumbled from their seats as cars fell and twisted. Some found themselves in icy water. Others remained trapped in wreckage. Then came fire from coal-burning stoves inside the cars. Flames spread rapidly through the wreckage. What had been a systematic disaster became an inferno. By the time rescuers could reach the scene, approximately 92 people were confirmed dead, though contemporary accounts suggested the actual death toll may have been significantly higher. In the next few minutes, we're going to explore how a bridge failed, why it failed, and what the disaster revealed about railroad infrastructure. This is the story of the Ashtabula Bridge collapse. The bridge that shouldn't have been built. The Ashtabula River Bridge was designed using relatively new engineering principles. It featured what engineers called a Howe truss, design, a structure that distributed weight across wooden and iron components in a lattice pattern. But here's where the problem began. The design was largely experimental. Engineers were still learning how these structures behaved under real-world conditions. The bridge hadn't been tested extensively. It hadn't been subjected to loads beyond theoretical calculations. What made this experimental design special was that it represented cutting-edge 1870s engineering. Railroads wanted to expand across America, and bridges needed to cross rivers. Engineers designed increasingly ambitious structures. But without extensive real-world testing, without understanding exactly how materials would behave under sustained loads, the bridges sometimes failed catastrophically. The Ashtabula Bridge proved that theoretical design needed to match practical reality. Modern bridge design requires extensive testing and analysis before construction, learning directly from Ashtabula's failure. The design flaws that no one recognized. The Ashtabula Bridge had fundamental design problems that contemporary engineers didn't recognize. The connection points between structural members weren't as strong as needed. The materials selected hadn't been tested for the specific loads and stresses they would experience. The design lacked redundancy. If one component failed, the entire structure could collapse rather than distributing the load to other components. These weren't obvious flaws to engineers of the era, but they were fatal flaws nonetheless. What made these design problems special was that they revealed gaps in engineering knowledge. Engineers didn't fully understand how forces distributed through complex structures. They didn't understand material fatigue, how repeated loads over time weaken materials. They didn't understand that theoretical calculations based on assumed conditions might not account for real-world variations. The bridge design assumed perfect conditions, perfect materials, and perfect behavior. Real-world conditions were messier and less forgiving. Maintenance failures sealed the fate. Beyond design flaws, the bridge suffered from inadequate maintenance. Inspections were infrequent and often cursory. No systematic program tracked the bridge's condition over time. Metal components corroded. Wooden elements weakened. The overall structure slowly degraded without anyone recognizing the danger. By the time of the 1876 disaster, the bridge was in worse condition than originally designed for. What made the maintenance failure special was that it represented a fundamental principle. Even well-designed structures require ongoing inspection and care. The railroad company had assigned responsibility for maintenance but provided insufficient funding and personnel. Adequate inspection might have revealed the bridge's deteriorating condition and prompted repairs before catastrophic failure. Modern infrastructure requires regular, systematic, and well-funded inspection programs, a principle largely learned from disasters like Ashtabula. The moment of failure, when physics met human hope. On that December night in 1876, the bridge failed during the train crossing. Whether the failure was triggered by a specific load exceeding the structure's capacity, or whether progressive deterioration finally reached a critical point, the result was the same: the bridge gave way. The train fell approximately 75 feet into the river below. The impact broke wooden cars into splinters. Metal components twisted grotesquely. What made this failure moment special was its sudden finality. The bridge didn't gradually sag or show warning signs. It failed completely and immediately. Passengers had no time to evacuate. There was no warning. The disaster happened in seconds. Modern bridge design and safety protocols require load capacity to exceed expected weights by large margins, so gradual degradation won't cause sudden failure. The Ashtabula Bridge had no such margin. The fire that made everything worse. Surviving the initial fall was only the beginning of the tragedy. The train cars caught fire from coal stoves and burning materials. Passengers trapped in wreckage found themselves in flames. Rescue was complicated by darkness, ice, and the complete destruction of the cars. Some drowning victims were trapped in icy water. Some burn victims were trapped in flames. The fire spread so rapidly that even rescue workers arriving quickly couldn't save many victims. What made the fire so destructive was that it happened simultaneously with the disaster, rather than being a separate problem. Passengers who might have escaped burning buildings on dry land found escape impossible from twisted metal wreckage partially submerged in icy water. The combination of factors, structural failure, fire, water, cold, and darkness, created a perfect storm of casualties. Modern trains have fire suppression systems and escape routes that the 1,876 train lacked entirely. The investigation: understanding catastrophic failure. After the disaster, investigators examined the bridge remnants and interviewed survivors and workers. They discovered that the bridge design was fundamentally flawed, that maintenance had been inadequate, and that no system existed to monitor the bridge's condition over time. The investigation revealed that the Ashtabula disaster wasn't a unique accident, it was a predictable result of inadequate engineering standards and maintenance practices. What made this investigation special was that it began a transformation in how American engineers approached railroad infrastructure. The disaster proved that expansion couldn't outpace engineering knowledge and safety practices. Bridges needed to be designed more conservatively. Structures needed regular inspection and maintenance. Standards needed to be enforced systematically. These principles, born from the Ashtabula investigation, became foundational to American infrastructure development. The Ashtabula Bridge collapse of 1876 represents a crucial moment when American railroads learned that ambitious engineering needed to be grounded in understanding, testing, and maintenance. What's remarkable is that this disaster taught lessons that the railroad industry applied immediately and that persist today in all infrastructure engineering. Modern bridges are designed with large safety margins, undergo rigorous inspection, and require documented maintenance. These practices exist because of what happened in Ashtabula. The next time you cross a well-maintained bridge, remember this. Over a century of systematic bridge improvement and rigorous safety standards arose from a single catastrophic failure that claimed hundreds of lives. If you've appreciated this story about how engineering learned from disaster, please like this video and subscribe for more railway history and lessons.